Good morning, everyone. Thank you for joining. This is Cassie Stumo. I am the Senior Digital Marketing Specialist at EAC. We'll start off today with an intro of EAC from Vinny, our Ansys Account Manager, and then Rod Scholl, our Ansys Technical Account Manager, will take over the presentation. Everyone gets a recording of the session. Pending any technical difficulties, please ask questions along the way and we'll answer them after the presentation. I will hand things over to Vinny now to give you an intro.
Awesome. Thank you so much, Cassie. Rod, you can go to the next slide. And yep, just a quick intro. I'm Vinny Lamovic, Ansys Account Manager here at EAC, for those of you that don't know me. Just to go ahead, next slide, Rod, to get things started off with a quick background of who EAC is and what we do. Our mission is to transform the way that companies design, manufacture, connect to, and service their products. Now, some of you out there have worked for us for many years, heard this before. Some of you might be new to you and just thinking, okay, great, but what does that mean? Well, if you look at this slide, it means that everything we do to help companies build better products is connected throughout both our organization at EAC and yours as our customer. We don't like seeing ourselves as just another value-added reseller or just a software vendor. We like to see ourselves more as a highly trusted business consultant. And if you look at some of these areas where we're capable of providing support, you'll see that business consultant claims start to take shape a little bit. We're Platinum PTC partners, preferred Ansys partners, and we're also Formlabs partners as well. So not just software, but hardware providers as well. And you see on the engineering side, we have a full staff of engineers that can assist with any product development consulting or questions that you might have as you're trying to get new designs out the door. We even have an implementation staff that's ready and able to come on site to ensure that any PLM launch that you take on is nothing short of successful. We're headquartered in Minneapolis, but we are spread pretty evenly throughout the country to ensure that we will always have someone local that you can count on in a pinch. Our goal is that we like to have people spread out enough where no matter where you are, if you need someone on site in one day, we can make that happen. Go ahead, Rod. Now, here's a little more about the Ansys side of things. Most of you probably think of simulation when I say the word Ansys, and that's exactly what we want to hear. Ansys has taken great pains since their founding in 1970 to do one thing and be the best at it, and that thing is simulation. It's the only thing they focus on, and it shows. Their customer support system is unrivaled, with over 450 PhDs on staff in over 70 offices in 40 different countries. I've actually heard firsthand a few times from some of our applications engineers that they like getting difficult problems to solve because they relish in the challenge to put it up against their software. If you have a problem, there's nobody better to help you find a solution. Go ahead, Rod. All right, now, if you do choose to focus on one thing, you had better be the best at it. And Ansys' reputation absolutely backs them up here. They're 3 times larger than their nearest competitors, and 96 of the top 100 Fortune 500 companies use Ansys. I like to repeat that just to kind of let that sink in. 96 of the top 100 Fortune 500 industrial companies are using Ansys. That's just an unbelievable statistic. And the big reason for it is on the bottom half of the screen, is that Ansys is completely CAD agnostic. They can work with anyone. They don't discriminate between people using Creo, SolidWorks, Autodesk, CATIA. The simulation software that they provide can work with any CAD platform without any issues whatsoever. Go ahead, Rod. All right, now I've been using the word simulation a lot, and some of you might be thinking, okay, awesome, simulation, but how does that help me? Maybe not as new as a term in the electrical field for some of you, but I'm here to tell you that you can use simulation in your field. I work with companies that use Ansys from the first design sketch all the way up to when they're running production parts. You'd be amazed at what's possible by having a conversation with one of our applications engineers. Some of the things listed here are just to help give you an idea of some of the ways that we can help you guys throughout design. We work with autonomous vehicle companies all over the world, help them reduce their validation time from 10,000 years to just 2 or 3 years with some of the simulations that we enable them to run. And our simulation results are now accepted by the FDA, ISO, ITAR, and many EMI and EMC compliance certifications that would normally require months to years of testing. So with that, I hope I've given you some useful background information on both EAC, Ansys, and what we can do. And this is where I will tag in my colleague Rod Scholl to start talking more specifically about Ansys Sherlock and what we have for you guys today.
All right, terrific. Thanks, Vinny, for that introduction. Appreciate it. It's always nice to start with a products overview slide. There's so many different products in the Ansys suite. In fact, so many that it's not even this product that we're looking at today. Sherlock isn't even populated on this slide, but it's in the electronics category, separate from structures and fluids. And of course, multi-physics is where Ansys has carved out a unique and dominant place in simulation tools. So a lot of what we'll see today, we might touch on how it can be leveraged in a multi-physics environment, taking these results and bringing in or coupling them to other physics solutions. So I plan to walk through some slides on Sherlock, showing its use case, showing how it's used, a couple case studies, and then we'll boot up the software just to get a feel for the interface and what the workflow is like. So with it's true with all designs that there's been a decades-long push from designing in the prototype stage to designing earlier in the design cycle, and simulation has facilitated that change or that improvement and all the cost savings associated with it. PCB design has lagged behind to some extent, nearly due just to the expense of doing simulation, mechanical simulation and thermal simulation of printed wiring boards, just because of the many details that of what it would take to get a decent simulation model. So smeared property models were the standard for many years, and still a lot of people are still either not doing analysis on their circuit cards, or they're just using a solid rectangular plate and using that to try to estimate reliability and performance under environmental loads. But it's been the cost, and essentially cost on the pre-processing side of building the models, which has slowed people down. And that's where Sherlock comes in. Of course, without Sherlock, you're modeling later in the process, or you might be actually testing boards and finding failures as you raise environmental temperatures. Your percentage failures start to go up, or during vibration testing. That's so late in the design cycle because you've already got a piece of hardware, and that can be very costly. So it's actually very easy to show return on investment with this software, with any companies that exhibit failures even occasionally, because all it takes is one failure to ruin a program schedule, and the costs associated with that are sometimes astronomical. And now that there's a tool in place which lowers the cost of simulation, we're seeing a lot of people adopt this tool. It's wonderful, and of course Sherlock was created by a company, now I'm forgetting their name, I shouldn't be. And Ansys purchased them, DFR, and they still support the tool and expand on the tool, and so it's just growing in the marketplace. And of course, what we're trying to do is go with eventually develop stress information, apply some reliability analysis, and come up with life prediction curves. That's the final output that one wants from a design perspective from Sherlock, is what's the percent failure over what time period for my design. So we have enclosures, we have the printed circuit board assembly, and then combined into a system. A lot of people use Sherlock just at the printed circuit board level, but you can bring in enclosures and shells as well to have those the stiffness of those components represented in the system. This is a nice view of the what I think one of the most valuable output slides of Sherlock. And we'll take a second to appreciate it. Down here on the bottom, we have a lifetime in years. Up on the top, we have a probability of failure. And this gray bounding box is specified by the user for how they want a component to perform. So in this case, we want to have less than 10% probability of failure over a 10-year life. And each of the curves representative are different applied loads to the system. So the green one is a plated through hole fatigue loading due to thermal cycling. The blue one is solder fatigue. Then there's vibration fatigue up in purple, and all the individual loads combined into a single overall combined risk. So you can do just a single analysis, but as you get further in the design cycle, or as your company has more well-defined environmental conditions, you can add those all in together. So the power of Sherlock is really, I mean, it's in throughout it, but for me, I'm most impressed by its pre-processing capabilities. If you could generate this solid model quickly, then you might be able to achieve these same analyses in Ansys. It, of course, wouldn't be as automated because Ansys is more of a general tool. I mean, and by Ansys, I mean Workbench Mechanical or Classic Interface or Discovery AIM series. But populating this image up on the right, creating that image from the information coming from electronics design is where the expense of simulation has historically come from. And that's the pain point Sherlock set out to remove. But of course, it also automates the analysis and does report generation and easy post-processing. So all that's included in one interface. The way this is achieved is through an extensive part library. I've heard the number 300,000 individual components, not including packages. I'm not sure the number of those, but a ton of those as well. So because the naming conventions in electronics world is relatively standardized, Sherlock is able to read the ECAD files, the pick and place parts list or the bill of materials, and index a database to populate those components onto the board, including their placements. You can work with your own library if something is missing. You can and keep a local library of components, but it's pretty surprising how much just the first import is successful. Of course, you have to go through each part and make sure it's what you want, because some of the entries are labeled as guess, for example. So it recognizes the package or the package thickness. It's using a default ratio. If you have that information as a component you use a lot, you might switch it from guess to the actual thickness. And the origin of all the data is tracked here and color coded off to the right. So within the ECAD file, such as an ODB++, there's sometimes redundant information and sometimes conflicting information. If you're getting ECAD files from a supplier or someone external to your company, each time is going to be a little bit different for which of the files are more accurate and which ones are just dummy placeholders put in by their design tool. And so you have the flexibility to control prioritization of this parts list. But also, if it's internal, I think you'll develop a pretty smooth system if you're doing the electric design internally, so that these parts become populated and the prioritization is correct. So orienting ourselves within the overall design flow, Ansys Sherlock can be used as just a preprocessor to develop those boards. and the attached components. And then you could use that generated model to do electrical simulation, thermal simulation, or mechanical simulation. So SI wave, ice pack, mechanical, or you can continue through to the reliability analysis within Sherlock. And Sherlock will take inputs from the systems above here for its reliability analysis, as well as, of course, doing these same or some of these same analyses internally. This one takes a minute to stare at, but I think it's worth, again, just seeing where the tool would be used in your design process. You're going to start here with the input data for after the electronic design is first done. It's going to parse through the Sherlock library to create a design and analysis. So bring that over into pre-processing. You can include life cycle conditions. If you wanted to, you can bring it over to the Ansys suite and do more complex thermal, vibrational, and shock analyses, nonlinear analyses, or anything that's particular to your design. And of course, you can bring things back in on post-processing from any of these complex analyses, bring in the strains and the placements, temperatures, and use the Sherlock reliability physics for reliability predictions. So when it comes to reliability for solder models and other electronic joints, there's been a slow and moving technological history between how to calculate that. And it starts back around Steinberg, I think that's like in the 50s, and Darvaux models into Engelmeyer. And Engelmeyer was sort of the latest and greatest, which uses a strain range, so Coffin-Masson type fatigue curves and an allowable strain for each of the locations on the board. Battau, if I'm saying that right, switched that over to a strain energy method, and that's what Sherlock uses. So there's some papers showing how successful that has been, but the point is it's using the latest technology to take the predicted strains at all these board locations and come up with predicted fatigue lives for all these different types of connections. So that's a little bit of theory going on behind the scenes. Obviously, if you want to dig into that and that's important to you, we can have a more technical discussion. So we see how it fits into our design process, but what exactly can it do is the question. So solder fatigue at the board level or system level, it can predict natural frequencies. You can apply mechanical shocks, random vibration, your PSD, harmonic vibration, doing the plated through hole fatigues. CAF is like a migrating, substrate materials like copper migrating during an electric field, a sort of advanced analysis, but it's been implemented. Heat sink modeling, wear outs of capacitors, especially if you have that data, of course, from the manufacturer. You can extract trace models from within Sherlock. Integrated circuit aging and wear out, again, if you have information on that chip. And I should also point out that it's a locked IP model, so that you can work with your suppliers and downstream customers while still locking some of the intellectual property within the, for sensitive information. So when to use it within the design process, you start with your hardware specs from the customer, build a functional block and have to make decisions on the housing and the connectors, come up with an actual board. The more you use Sherlock, the more it'll be involved in your initial part selection, because its parts library will show you the different types of attachments and joints. You'll begin to get a feel for which parts have superior fatigue lives the more you work with them. And then, of course, initial part placement. This is what's, in a typical design process, you get one or two guesses at that. And Sherlock makes it so you get many guesses quite inexpensively. And of course, part placement is huge for any of the mechanical shocks or vibration cases. It can also matter for thermal as well if you have some high temperature chips. And then developing a final layout, producing the bill of materials. There's a brief slide on the locked IP model. If that's of interest to you, we can give more details to you of what can be hidden and what those input outputs look like. So many times, this might be redundant at this point, but I still like the slide. I always think of electrical circuit design, and since I'm a mechanical engineer, I think of that as somebody else's territory and somebody else's problem. Once in a while, when we have to include it, as we mentioned before, I've used smeared properties on a rectangular board and not really know the actual stiffening components, stiffening effects of the installed components. But that's no longer the case with Sherlock. You're going to, if you're in charge of the reliability of a product, the mechanical reliability or electronic reliability of the product, I think Sherlock is the tool that you would use. If you're involved in the testing, a lot of the cost savings that we see are done on the test side, scrap rates, the cost of building tests. If you can show some tests aren't marginal, then you don't even have to perform them. You don't have to build certain fixtures. People can save millions just on the testing side. So if you're new to electronic board design, I mentioned already how part placement is important, and it's sort of a competing issue between the traces and the power generation, heat dissipation, and then the mechanical requirements. Generally trying to avoid placing things in the very center of the board, which is often the flexure points, unless you have some posts located there. But for surviving mechanical shock, where should we replace the IC chips? So here is an image of a Sherlock output. You can see the displacement map of a shock profile. This U27 chip has been placed right in the center. And you can see off to the left that you end up with a reliability of around 100% failure by 10 years and 20% failure at 3 years time. By sliding the chip to the left to another location on the board, you can see dramatic improvement in the life of the product. Similarly, on this one, they've changed the support locations, changing the profile of the displacement and leaving U27 in its original place, and that has an even better effect on improving life. So in this case, they also changed the potting underneath U27. So the build times, as I said from the beginning, changed from 2 weeks to 45 minutes. I think your first time through it might take a couple, 3 hours because of familiarity with your individual components. But as you become more familiar, I think 45 minutes is too long. It just doesn't take that long to import models that come in right away. And you just got to review, depending on how many chips are on your board or how many components are on your board. It always makes sense to review them to familiarize yourself with them. And all this as an input makes, so this is a nice tool to combine with your ice pack and your SI wave for your mechanical, because it does that pre-processing for you. And in the end, we're saving costs by reducing warranty returns in the field. If this tool interests you and we have to justify the cost of maintenance and purchase, looking at warranty costs on returns from electronic failures, those add up very quickly. So it's an easy place to sometimes find the ROI, as well as testing costs, which I already mentioned. And then just in terms of design cycle improvement, it takes the design process from months down to weeks or even days if it looks good out of the box. It can verify that. And sometimes time to market is what's most important in electronic fields these days. I wasn't sure where to put these slides, so I threw them in here. Just as a reminder that there's this Ansys Learning Hub. When we start talking about new tools, it always seems like a daunting task to me to have to dive into something, a domain that I'm not familiar with or a tool set I'm not familiar with. And the Ansys Learning Hub is a pretty affordable tool to give you, a year's worth of access to self-paced learning classes and tutorials to lower the cost of ownership and learning a new tool. So real world success stories. This is a case of eliminating the testing costs, $350,000 with each test that they remove, saving $1.4 million. Again, because test fixtures are expensive, and then performing the test, especially at high volume, is also expensive. I don't know how to stop the auto forward here. Pause. So here's more test costs, $7.5 million saved by GSM. I think the other one was AAM, and then this last one is CommScope. Of course, companies that are doing this day in and day out, they just couldn't do their jobs without Sherlock, but we're seeing even small companies leverage it to make their components more reliable. All right, with that being said, I think it'd be nice to show you the tool just so you get a feel for what that looks like. It's nice that this is a relatively quick tool, so we can do things live. I don't have to load up existing analyses. I might default to that, but let's just start with a clean open Sherlock page, and I'm going to import an ODB archive. So if you're not familiar, ODB++ is probably the most common file format for ECAD, and it's not really a file, it's actually a zip directory of a bunch of other files. And I've got one here, and we will call this for webinar and card 1. And so it's going to read through those files, and essentially what it's going to do is an import on what's primarily ASCII text. In this case, the mapping is pretty direct. We've only got 3 column headers. It's pretty obvious what they're mapping to because this is a clean ODB++ that I'm using. If you get an ugly one that comes from a manufacturer that is using different incompatible tools for their design, sometimes there'll be multiple description, multiple part numbers, or just blank columns that don't have any headers, and you'll have to mark them in. But I just wanted to point out that the import process is sort of full featured to let you automate those imports as much as possible. This is the data that it's found. I'll click import archive, and it's bringing them in. So I'm going to collapse some of these and kind of get a look at what's in these folders just so we can orient ourselves. This top one is the project that we're working in. Lifecycle are essentially the environment and the boundary conditions, and we'll come back to that. Card is, card 1 means that's just the ODB++ file I brought in. And we have the files that are brought in. There's going to be some inputs we should define, some analysis that will run, and some results that we'll view. So on the input files, one of the nice things to do is let's just look at a copper layer. So I've double clicked it to bring up the layer viewer, and I'm going to toggle off some components, and we can see the copper trace that was present in the ECAD. And actually we can see all of them if we want. Remove the power ones there. but top and bottom, and we'll just look at the top for now. So here's the top copper layer and traces that are present. Now let's come down here to inputs where all these files have been brought in. Let's look at the stack up. What the stack up has done is gone through those individual layers and laminates and come up with aggregate material properties automatically. It's assessed the volume of copper, and it's adjusted the CTEs automatically and the densities. So this essentially composite material now has 11 layers in it with the different copper contents and laminate contents. And of course, if you wanted to adjust these for a particular design, you could as an improvement or as a design change. If we go to the layers, go back as well. You probably won't do much editing here in this. You might do editing on the ECAD side, but the kind of editing you might do would be to change part location or orientation. So if I go to edit components, get rid of the bottom, and I can even get rid of the copper. We'll turn off the labels just for fun. And so I can pretty easily move things around on the board. Obviously, there's no room for this one. So let's cancel that. But if I want to rotate, a bunch of resistors, oh, missed. Resistors sometimes don't come in with the correct orientations. Most things come in with the right orientations, but there's an inconsistency within the standard for them. We can see I can move through holes around, the mount points around if we wanted to, or change their size. But you can see it's pretty easy to make minor changes on this board to do design changes. I think at that point you would then send it back to ECAD and they could update the traces for the design that you determined would have acceptable reliability. Now the other big component here, we've talked about the board coming in and the component positions. Let's talk about the components themselves. And so I've gone over here to parts list. This is not that big of a board. This is a couple hundred, maybe 100 components on it. The color coding here is important. It tells you the origin of the information, where it's brought it in from the ECAD files, and a lot of them are orange and are therefore a guess. The package DB file brought in some of the package names, part numbers came in probably from the bill of materials. This parts list you're going to spend some time working with, and so it has some features, such as filters, and you can edit properties within it. You can edit individual properties. And for example, you might come in and change the solder material. You might change the solder thickness. Of course, you could manually edit location if you wanted to. The definition of the leads, the different lead geometries that come standard, those were defined in the package DB. And there's also the ability to modify multiple parts together so that it's not a manual process. So just want to point out, you have a fully featured interface to work with your parts individually and edit them and make changes as required. Now this parts list, I'm going to right click here and go to update parts list from part library. Now you have a local library and the Sherlock library. So I'll just use part numbers here. This is going out to the Sherlock library, the 300,000 plus components, which is being updated with different manufacturers and data. And you can see a lot of these fields have turned green, meaning that it has found those components and populated more information within each individual component. So that's the creation of the components. And first time through, you might just click solve without even messing with the parts list, just to see what you're working with. And as you work with the model, you would add accuracy. So you have component definition, you have the board layer definitions, and their placement. The next piece of information we need is the loading and the life cycle. There's a default one in here, but I want to load one that I've already created. So they're not hard to build, and I can imagine you would have a standard load library that you might apply, or this would come from a specification for your component. And so in order to calculate the life of these of your circuit card assembly, you can choose just some of these loads or all these loads, but defining them all within the life cycle is handy. So within the shipping load, we have an XYZ direction. You can see this is PSD, this is random vibration and G squared per hertz, and comes in with a file. You can edit this profile, tabular edits, temperature, operating temperatures, uniform operating temperatures, the environment cycles going up and down. This has only one load case in it, but you might have multiple starts and stops and long dwells. Pumping, this was on a mechanical part that actually had a known G loading profile. So essentially a shock profile, and this one's going to repeat, 100 cycles per hour. So this is where you would put in duty cycles, mechanical duty cycles. Now you might have some shocks. I guess there aren't any shocks defined here as well. This filter change looks like is a time history transient. So you can see the options for editing those individual environmental events. So with those defined, we have the input, or we have the board and we have the inputs. Let's show you what the analysis looks like and how quick it is. The longest one is natural frequency. So I'm going to kick it off now and say edit properties. It brings up some questions like how many modes do I want over what frequency range. I'm just going to accept everything and say save and run. You can see this little clock going down here. We'll do some plated through-hole fatigue. We're going to add the first two, or let's add all three environmental loads. We'll run fatigue on that. And let's do solder fatigue. And right now it's using this, let's use SM100C, and we'll run all three conditions. So plated through-hole fatigue is done. Actually, it looks like the others are done as well. If we look at the results, we have all sorts of problems with plated through-hole fatigue. Everything is red. If we go to life prediction, we are not meeting life. Time to fail, we can see there's quite a few components, or sorry, holes, because it's the plated through hole. Quite a few holes which are failing the fatigue criteria. And a tabular view, we can look and see which of those are the worst. In this particular analysis, I just did this earlier, so I know this is all coming from the pumping, I believe. So if we turn that off, now we can see, oh, the life isn't much better, but plated. All the components are passing the plated through hole requirements, but it's still marginal, or still yellow. All right, so greater than 40 years, so that's enough. Let's look at the natural frequencies. There's a summary. If we want to actually view the natural frequencies, this pulls up a viewer, so there's a second for this license to check out. Now, when we submitted the natural frequency analysis, by default, it's submitting an Ansys job in the background. So it's created the file, it's run Ansys, it's solved it, it's brought those results back in. So that you can match Sherlock to different solvers, but in this case, we're using Ansys. And right now we can look at the individual mode shapes on the board. It's nice to see the parts populated on there as well. For visualizing where components might need to move and where high strains are. You can export these types of results into PDF, for example, for sharing with the team. This is just kind of a nice feature of PDF that you can now rotate PDF, have dynamic, oops, that's not that one. So if you want to share information easily, PDF is a nice way to do it. So although these are nice 3D pictures, it's worth showing that within our layers tool, because I've done this analysis, the FEA results are in there as well. And let me add in the components. And so that's maybe it. You know, the 3D view is nice, but this maybe is more typical usage to see how your deflections map onto your individual components. Let's go down to solder fatigue again and view those results. So solder fatigue did not match currently. If we look at the table, what are we looking at? A lot of these have a life of around 3 years. U1 and U2 seem to be the worst. So a typical design process might be, you probably have to change a bunch of them. So maybe you would select U1, U2, and all these resistors. Go back to your parts list. And for U1, U2, we would change perhaps the solder to a defined higher grade material. And then we can go back and rerun the analysis. So it's using the same defaults for everything else, but since we've specified the solder material for U1 and U2, now we can see U1 and U2 have increased their life. They're up to 9.43 years just by changing the solder material. It might be worth it to go back and change the solder material for these resistors, or obviously there's a lot of other design changes one could make. So that's what I wanted to show you there. Let me import a fully solved project here and talk about project reporting, because that's sometimes the least pleasant part of our jobs is making the report. You'll notice this analysis has green check marks. They've done every type of analysis on this particular component. So under report, we can generate a CCA report, tell it what we want to see, and I'm going to say everything. This will take a minute to pull up. But in terms of cost savings, a lot of times it's not even cost savings in documentation because people just don't document because it's too difficult. So it's not just a cost savings in this case. I'm gonna have that opened up. I thought I had that closed. Here's the report. And this automation saves countless hours and allows a report where we can add in a few paragraphs later to describe observations, conclusions, and desired changes. So this type of analysis, turnkey type of analysis, really lends itself to report writing. And so this is a terrific feature. So everything we've talked about so far shows life cycles and inputs of just environmental temperatures and shocks. But one of the big things that we become concerned with on some boards is thermal profiles within the during operation. you can go through and assign temperatures to individual components, but many times that isn't known. One way to do this is to add a thermal image file. So I'm importing a thermal image. Let's view the file. This was done with a thermal camera on this particular board, which we can now use that thermal image as an input. So this is a thermal map as an image. Let's move out of the way. Minimum temperature is 30, maximum is 47. So I'm doing this with a thermal camera image, but you can imagine you could do this with an FEA image from a supplier, or you can of course read thermal results from an Ansys tool. But if you didn't have that and all you had was an FEA report, you can still import those results. And now for the mapping, we actually have to map the board. Just kind of fun to do. Oops. So you tell it where the board is at. And then the contour scale. Align the legend. And so with that being saved, let's go back to our layers image. Get rid of that. Oops. And apply a thermal map. So whether it comes from an FEA analysis or a thermal camera, you can see how this is quite valuable for maybe moving or seeing what components are being most affected by the temperatures. The last thing I want to show you, don't have a ton of time left, is as we've used it as a preprocessor. We've stayed within Sherlock this entire time to do our evaluations, but sometimes people just use Sherlock solely as a preprocessor. And that is where you can go down to analysis, for example, and go to, let's say, natural frequency and export FEA model. And there's different formats right now. I've had it selected to a WB, it's a journal file for a Workbench. And I can tell it, for example, on the printed circuit board right now, it's doing a merged, which means it's merging all those 11 layers into a single property. Sorry, that's mesh type. The trace modeling, where you can forget where that is, where you can specify the individual layers, whether you want to show individual layers or whether you want to merge it all into individual layers. Oh, there we go, uniform. So layered, uniform elements, layered elements. And then click export, and you can control everything that you want exported, whether or not to include the drill holes. It takes about 3-4 minutes to do so. So I did that in advance. Brings up this Workbench model. So all I did was click export, and it launched Workbench, ran that journal file, and created the associated geometry. Well, that's pulling up here. I have an image of what it pulled up. So that you can begin working with this as a normal mechanical file at that point. So that's a lot of the capability. There's of course many that we haven't touched on. This isn't really meant to be a demo, but as an introduction to the tool, if this seems like something you might be able to use in the design process, we look forward to a chance of having just a conversation to know how you might use it. And then from there, we can build an actual demo to show you the capabilities which apply in your particular situation. With that, I think I'll open this up to any questions that we have. If there's anything you guys want to submit via, actually Cassie or somebody, maybe tell them how to do it, or maybe it's apparent how to do it. But if you have any questions, we're happy to try to answer those in the time remaining. And Vinny, do you have anything that you wanted to add?
Yeah, so if anyone wants to submit any questions, go ahead in the queue. You should see a questions panel, or you can write in the chat, either way. We do have a question that came in. It is, what method of calculation is being used for fatigue life?
Yeah. I think that maybe that came in earlier. That was, so, Coffin-Manson was used previously in analyses for strain-based fatigue life. But in this case, we're using that Plateau method, and Dr. Plateau actually worked with DFR in the development of this, and there's some papers, but it's a strain energy based evaluation of the components, attachment, the attachment points. Now, fatigue life on individual components or IC chips, those will come from the manufacturer as different various curves, sometimes SN curves or strain curves or temperature curves, and so those would be on a case-by-case basis.
Okay. Our next question is, can Sherlock model mezzanine boards?
Yeah, mezzanine boards or multi-layered boards, where boards are stacked together, usually separated by posts or other attachments. Yeah, exactly. So you could bring in, right now we brought in a single board or a single card. You could bring in multiple cards and then specify how they're attached to one another, and thereby have a full analysis of your mezzanine assembly.
Great, thank you. And then we've got somebody asking what the source of the requirements are for environmental loading.
Yeah, so if we go back to Sherlock, for life cycle, I had these populated in a file. I guess that's a good question for a discussion. If your company is new to determining these loads, like your failures don't have known origins, or you're the OEM and no one's giving you a spec for these, we can certainly give some advice early on and point you to some resources. So for shipping loads, there's known load curves for FedEx trucks versus over road or off-road conditions. So that is part of the engineering that happens in the background to know what those cases are. And of course, if you have a customer spec, sometimes they just give you a random vibe profile. If this is going on an aircraft, you'll be working in MIL standard 810 most likely. So they come from a variety of cases. If that's new to you, then we're happy to point you in the right direction.
Awesome, thank you. Do you want to move to I think we've got one slide where Vinny can just wrap it up and talk to, where do you go if you have questions on Ansys Sherlock?
Yeah, you can reach out to either myself or Rod if you have any questions. You see my email right there. If you'd rather have a phone call, shoot me a quick email. I'll be happy to provide either my cell or my direct office dial.